Okay, so the last part of our non-parametric statistic is what we call as the Kruskal-Wallis test. Okay, and we know that the pair for the Kruskal-Wallis test for the parametric method is the ANOVA, one-way ANOVA. Okay, so one-way ANOVA, we are talking three, four and above, three and above number of population involved in our hypothesis testing. So if you have three and more population that you need to test simultaneously, and what test should you use? Then if the data is not normal, then that will be the main reason. If the data is not normal, then you're going to choose Kruskal-Wallis test. Let's see what are the details about this particular test. Okay. Now, if you can see from your textbook on page 148, okay, among others, Kruskal-Wallis test is a non-parametric method that works based on rank. So we are talking again about rank. Last time we also talked about rank, the non-parametric statistic. Okay, so we are talking the sign test. We are using the rank of the plus minus. Okay, whether the median value will be above or below the hypothesized median value. The same goes to man-Whitney test. Okay, when we have two populations, so we are going to rank the data as if they are coming from the same sample, and we rank them accordingly to the smallest, from the smallest to the largest. And what happens if you are dealing with Kruskal-Wallis? Okay, same thing, you are going to rank the sample or the observation value. It is also called as Kruskal-Wallis H test. So another name for Kruskal-Wallis test will be Kruskal-Wallis H test. That's why later on we are going to use the indicator of our test statistic using using the H value. Okay, and this test is named after William Kruskal and W. Allen Wallis. Okay, these two guys come up with this particular method of testing three or more population. Now, this method applies under this condition. Okay, involve three or more independent samples. It must be independent. Means that the first population does not affect the second population. Okay, the same goes to the second and third, first and third. Okay, independent among them. And then we are going to compare, and then we are going to see whether they have equal or unequal size. So you can have equal size in your sample, or you can also have unequal size. Okay, both are possible. Second, the data does not meet the parametric test requirement. Means that the first one, data are not normally distributed. Means that all the three or four populations that involved in your test are all not normally distributed. Second, variances among groups are different. So in this case, you can have unequal variances. Unlike ANOVA, the variances must be equal. Then only you can use your ANOVA. If you have unequal variances, then you can use your Kruskal-Wallis. And finally, data measurement is in ordinal scale. Okay, in order. And next, the hypothesized parameter is the population median. So again, we are going to use our median value, okay, as our parametric value that we are going to have in our statement of the alternative ML. And the test is used to determine whether there are three or more samples originate from the same distribution. So the test is basically testing whether they are from the same distribution or not. So this is the gist of your test actually. But then when we test for the statement, okay, so we are referring to the median. But that particular statement refers to this particular concept actually. Okay. And last but not least is the assumptions. And then the assumption that you need to check before you can proceed with this test would be the first one, there must be at least 3 samples to be compared. If you have 2, then you cannot use Kruskal-Wallis. You have to use your man-Whitney test. If you have 1 sample, you're going to use your sign test. Okay? The sample size must be at least, so remember, it must have at least 5 samples. Okay, must have 5 samples or more. Less than 5 cannot. Okay, so this test cannot be worked for less than 5 samples. Means that the observation, so if you are talking about group 1, group 2, group 3, okay, so if you must have observation number 1, so let's say x1, x2, x3, x4, x5. Okay, if it is less than 5, let's say x21, x22, x23. Okay, cannot. It must be at least 5 samples inside your group. And last but not least, the test is always right tail test. Thus, the test statistic should be large enough to reject the null hypothesis. Why? In this Kruskal-Wallis test, our critical value, okay, is given by chi-square. Chi-square. Okay, given by alpha with the parameter alpha and k minus 1. Okay, what is k? It's your population value. If you have 3, then your k is 3. Okay, so chi-square test is almost like your F test. So the distribution of chi-square test is almost like F test. Okay, but F test works for only several population, but for chi-square test, so you are using this particular distribution, and your alpha value is the one given here, and this is your chi-square alpha. Okay, so it will be a right tail test, and if you wish to reject your null hypothesis, you need to have a very large test. Okay, you need to have large test statistic. That is your H. Okay, your H must be large enough so that it will be falls within the rejection region. So that is what meant by the second point. Any questions so far, class? Any questions so far?
No, doctor.
Okay.
No, doctor.
Okay, so if no, let us look at the example. Directly, we use the example so that all the concept that has been discussed on page 148 and 149, you can compare that when we discuss this particular example. Okay, now, example 4.7 on page 149. 3 machines A, B, and C are used in packaging of 1000 gram milk powder. Each machine is set so that each packet will contain on average 1000 grams of milk powder. Samples of 5 packets from each machine are randomly selected, and the amount of milk powder for each packet is measured. So you are talking about 3 machines, A, B, C. And then for each machine, in this case, they have same number of sample size, that is 5. So you have 1, 2, 3, 4, 5. So you have 5 samples for each machine. Okay, so in this case, you have K equal to 3. You have N1 equal to N2 equal to N3. That is equal to 5. And your total sample is 5 multiplied by 3. You have 50. Okay, now what else? The data set is given below and assume that the data is not normally distributed. At least you will be given this hint. Means that this is, you know that this is an indicator of non-parametric statistic. Okay, non-parametric method. Okay, so by using alpha 0.05, test the hypothesis that there is a difference. So this is your claim. There is a difference in the amount of milk powder packed by the 3 machines. Okay, so this is your hint for your conclusion as well. Now, let us begin with the solution of this particular example. You can have your step 1, okay, either you use all the sentence in your null and alternative. So if you are using your sentence, it will be sounds like this. The null will be there is no difference in the median. So the word median should be included so that it will what we call display that this is a non-parametric method. Okay, So there is no difference in the median amount of milk powder packed by the machines. Plural because refers to A, B, and C. Okay. In reference to your now statement, so your alternative would be there is a difference. Okay, in the median amount of milk powder packed by the machine. Or you can also write as median 1 is equal to median 2 is equal to median 3, because since you are not being given the hypothesized value, okay, so you are going to use this symbol. Okay, and for the alternative, at least one group median is different from the others. Okay, so you can use either this one or this one. Next will be the second step, obtain the critical value. Okay, so in our case, our critical value is obtained by using the chi-square test. So if you turn to your page of your textbook on page somewhere like 216. Okay, page 216. So you can see chi-square distribution. Okay, almost like f begin with 0. So we are going to look at this particular table for our Kruskal-Wallis test in order to find the critical value. When we say critical value, remember it refers to your alpha value. Okay, because your alpha is your rejection region. Okay, and for this case, since we have 3 groups involved in our test, and alpha given is 0.05. Okay, so chi-square for 0.05 with degree of freedom of 2 is given by 5.9915. So if I can show you how the distribution looks like. Okay, can you see, class, my F distribution? I'm changing my slide here. Can you see, class?
No.
No, huh? Okay, hold on. Okay. Okay. Hold on, I forgot to scan the chi-square test. I just snap the picture. Let me share you the picture. Okay, stop sharing. Okay. I coincidentally pick the full screen. Can someone tell me how I can show you the chi-square test, because since you are using different types of distribution, so it is good for you to make sure that you are referring to the correct distribution. Okay, so if you look at your page 216, so this is your chi-square distribution. Okay, chi-square distribution. So you have your V, that is your degree of freedom, that is K minus 1, and you have alpha in the first column, in the first row, sorry. So you are looking for 0.05, which is this one. Okay, so this one is your 0.05, and K minus 1 is equal to 2. That's why you get 5.992. Okay, so that's how you get your chi-square critical value. Now, let me share with you the slide again. Okay, so since we have identified our critical value, okay, now we move to our step 3, that will be calculate the test statistic. So in this step, you will need to assume that you are going to combine the samples and you are going to rank all the given observation from the smallest to the largest. And then once you put your rank value, you are going to find the rank for each of the machine. Okay, I purposely did not do the ranking just to show you how to begin with the ranking task. Okay, so you look for the smallest value. What will be our smallest value? Our smallest value will be what? 98995, 987. So you will have 987. You have two, right? So you have number 1 and number 2 here. But since they have ties, okay, if in case you have ties, take the average. So how? 1 plus 2 divided by 2, you get 1.5. That's why here you put 1.5. 1.5 here, 1.5 here. Okay. After that, number 3 would be 987.5. That would be number 3. And then you will have number 4, 987, 989. 989, number 3, number 4. And then you have two value 989. You have number 5 here. So 4 plus 5. Okay. Then you proceed with number 6 afterward. So 4 plus 5 divided by 2, you will get 4.5. So that's why you have here 4.5 and here. Then proceed with number 6. Number 6, next after 989 would be 99. Is it 990? Number 6, 989.5. This will be number 6. Okay, then number 6. Number 7. Number 7 would be 990. And then it seems that you have two 990. So you have number 7 and number 8. Divide by 2. Since you have only two 990, so you will have 7.5. So you have 7.5 here, 7.5 here. Okay. So then you begin with number 9. Rank number 9 would be 990.5, single value. So then number 10, 990.8. Then number 11. Number 11 would be 992. Number 12, 992, 993. 12. And then we have number 13. So it will be 995. 13. Okay, and then 995.7. 995.7. After 13 is 14. 5.7. 5.3. So 14 here. Okay, and then 15 here. So far, okay, class? You understand how you rank and if you have any ties between the value. So if let's say you have 3 ties, for example, let's say just an example, okay? Number 3, number 4, number 5. Since you are dividing by 3, you have 3 observations. So in order for you to find the average, you will need to divide by 3. So that's how you get the rank. So once you have got the rank, okay, compute all the sum of the rank. Okay, so in this case, you will get your rank sum for A would be 1.5 plus 3 plus 1.5 plus 6 plus 14. So you will get 26. And for your rank sum B, you will get 42. And for your machine C, you will get 50. Okay, and what does this value tells you, class? Okay, remember we are measuring the amount of milk powder put in every packet of machine A, machine B, and machine C. It seems that your machine C have larger value, almost similar to the expected volume of milk powder compared to machine B and machine C. So that's how you see what does the value of the rank given be. Okay, so the least amount of volume is given by machine A, and the maximum is given by machine C. That would be if we talk about the rank of some of each machine. Now, next you need to calculate the test statistic, and that test statistic is given by H, where the H is given by this particular formula. So just follow this formula. Okay, so if you have 5 or 4 population, then you will add here number 4. B squared and B. So proceed until whatever number of population we have. So in this case, we know our n is 15. So 12 divided by 15 multiply with 16 multiply with 26 squared over 26 squared over 5 plus 42 squared over 5 plus 52 squared over 5. And minus by, okay, minus 3 multiply with 16. And here you will get your H equal to 3.44. Okay, so that would be your step 3. And for the fourth step will be making the division. Okay, since we know that we are dealing with this particular distribution, and we have the chi-square alpha just now given by 5.992, and this is the rejection region. Now, since your H test is given by 3.44, which is smaller than your chi-square value. Okay, let's say this is your H, where value is 3.44. So in this case, fail to reject the null hypothesis because it falls within the non-rejection region. So here is the rejection region. Here is the non-rejection region. Okay, so fail to reject the null hypothesis. Now, our claim just now is there is a difference. Okay, so our claim is at the alternative. Now, since we reject the null, so we have sufficient evidence to support our claim. Okay, so how does your conclusion sounds like? So we have insufficient evidence. Sorry, we fail to reject. So we have insufficient evidence to support our claim. Since our claim is at the alternative statement, so we have insufficient evidence to support. What it will be our claim? That there is a difference in the median amount of milk powder packed by the three machine at 5% significant level. Okay, do you have any question, class? Do you have any question to ask regarding the last part of our chapter 4, Kruskal Wallis test?
So far, no, Doctor.
Okay. If you have no questions, okay, let me conclude your non-parametric method that we have covered in chapter 4 as well as in chapter 3. Okay. So the non-parametric method that we have covered so far, if you have one population, okay, so if you have one population, we are talking about sign test, okay, and the equivalent test for the sign test, if your data is normally distributed, so the non-parametric version is what we call the t-test and z-test, depending on the sample size. If your n is less than 30, then you are using your t-test. If n is greater or equal to 30, you are going to use the z-test. So that will be if you are dealing with one population. If you are dealing with two population, okay, so the non-parametric method is what we call as Mann-Whitney test, or we call it also as Wilcoxon rank sum test. So in this case, you are dealing with two population, okay, two population, okay, and the equivalent test for two population, if the data is normally distributed, that's why we call it as parametric version, is also the t-test and z-test for two independent samples. So remember this particular version of your two sample or two population test. And last but not least, for the three and more population, okay, so if you have normally distributed data, you're going to use your ANOVA. If your data is not normally distributed, you are going to use your Kruskal-Wallis test. Okay, so that's all for the Kruskal-Wallis test.